To find the growth rate of the population, if this is the population, then the growth rate will be the derivative. So to find the derivative, I'm first going to bring it up as a power of minus 1 because that makes y dash easier. I'm going to have minus 1 times 200 by 1 plus 19.5t to the minus 2 times by the inner derivative, which is going to be negative 0.5 by 19 e to the negative 0.5t. Clean this up a little bit. I have minus times a minus, so they'll become a plus. I have half of 200, which is 100, times 19 is 1900. I'll have e to the negative 0.5t. And with the power of minus 2 on this piece, it will bring it to the bottom. So 1 plus 19 e to the negative 0.5t all squared, which is actually what they gave us. Finding the range of the function. Now, there's a number of ways of doing this. For the function y, I'll just leave y visible at the top there. My preferred method would be to sketch it, actually, but there's a bit of work in that and a bit of extra knowledge. To look at range otherwise, you've got to consider, well, what your functions normally do and how they're affected, which I would still do by sketching. So let's sketch this thing. To sketch a function, you want to look at the whole thing. Start with your base function and then build it up. So I'm going to build it up like this to then get the whole thing. E to the negative x. E to the negative x looks like that. The 0.5 will simply give us a bit of a stretch out from there, but it won't change the fact that it goes through at 1 and that it asymptotes down at 0. So that's e to the negative t. If I'm going to do a 19 version of that, what that will do is it will stretch us up from the axis, and instead of being 1, everything gets times by 19. So that becomes a 19, but we still maintain our asymptote to head towards the 0. If I would add 1 to that, however, to get the 1 plus 19 e to the 0.5t, then instead of coming through at 19, we'll come through at 20, and instead of asymptoting on 0, we'll asymptote on 1. So now I'm looking at a function that looks like this. And if I were to do a 200 over, I've got to think about my largest value and my smallest value. My largest value is 20. 200 over 20 is 10. So that means the first value I'm going to have is 10. And basically the 20 comes down to the 10, and all the other numbers would climb up from there as they're climbing down towards this 1. And 200 on 1 is 200. So what I would have then is an asymptote at 200 and my function travelling out like that. Now I've got the added benefit of having sketched my function. I know that my range, my y values, is going to be from 10 inclusive to 200 not inclusive. Show that the rate of growth of the size of population can be given as such is just an algebra game. When y equals, it's ugly algebra, but it's still just algebra. So start with the initial y value. What I want to do is go y on 400 times 200 minus y and say that equals 200 on 400, so y on 2 minus y squared on 400. Now y on 2 would be 100, 1 plus 19 e to the negative 0.5t, minus y squared on 400. Now y squared is going to be 200 squared on 1 plus 19. Same thing again. Now if I'm dividing that by 400, then that's actually just going to put 400 into the bottom. So I end up as such. And now what I've got to do is fiddle with it until it looks like the function we were given up here, y dash. Oops, that one. That's y dash. That's what I've got to try and make it look like. So single fraction, I've got two fractions at the moment, which means I really need to create a common denominator by calculating this top and bottom over here to make the squared. So that'll be 100, 1 plus 19e to the negative 0.5t on now if I do 200 squared divided by 400, the answer is 100 again, so that's going to be 100 on. Now I can see that I have a common denominator going on over here, and I have one lot of 100 plus 100 of these minus one lot of 100, which means I have 1900. Because the common denominator I just added across the top. And just to finish that off, I'll say equals dy dt. Now, to find the size of the population, when it is growing at its fastest, we want fastest growth equals max of y dash function. And since the y dash function is equal to y on 400, this one, I could actually find the maximum of this in terms of y. I don't even need to care about in terms of time. This is a frowning parabola. It's a frowning parabola with roots when y is 0, so basically y would be this axis with y dash being that axis, roots of 0 and roots of 200. Now, if that's what the parabola is looking like, I know that the maximum will have to occur when y is 100. And so the size of the population, when it is growing at its fastest, it will be growing at its fastest when y is 100, and y turns out to be the population. Done.